So, we will discuss today the semiconductor laser. Like in the last class, we have discussed how a diode is formed, how p-n junction is formed when we take two p and n type different materials. So, we have seen that energy level diagram, and entire working of this semiconductor laser, that is related to understanding the energy level diagram, and we have seen energy level diagram of a p-n junction diode. So, now you think of a p-n junction diode made of heavily doped semiconductor. Okay. To make a semiconductor laser, we take a diode made of very heavily doped p and n type materials. So, how much heavily it is doped? For that, you see, you have this p type, okay, and when you make it p type, then we create holes in the valence band. Okay. So, when you create holes in the valence band, then Fermi level shift downward, it approaches the valence band top. So, when we keep on more and more acceptor impurities, let us make it more and more heavily doped. So, with doping, Fermi level comes down. So, when you make doping very high, then what will happen? The Fermi level will merge into the valence band. It will come inside the valence band, and the doping level is so high that part of the valence band appears to be empty, because when you create a hole means one state is empty corresponding to one hole creation. So, when you create more and more holes, then situation will come that it will appear as if we have vacated some portion of the valence band, okay, and that will look like something this. Okay. So, valence band will be shown like this. Okay. This is the valence band top ye hai, but below the valence band top, part of the energy band will be vacant. It will appear as if it is partially filled band. This is the level of doping, heavy doping we do in p type material. Similarly, you have n type material. Okay. In n type, Fermi level approaches conduction band, and when we make more and more doping, heavily doping, then situation will come that Fermi level will merge inside the conduction band. Okay. And that situation will appear something like this. It will appear as if thin layer of the conduction band is occupied. Okay. So, heavily doped region will be shown like this. Okay. This is the heavily doped p and n region, and we have to think of a p-n junction diode made of these materials, heavily doped material. This heavy doping level, it is called degenerate doping. Okay. Heavily doped material doped to this extent, so that Fermi level lies inside the energy bands. Okay. That level of doping also referred as degenerate doping. Okay. So, this is one of the requirement that we have to make the semiconductor diode consisting of degenerate p and n type materials. Same level of doping is done in tunnel diode, Zener diode. If you have studied in some course tunnel diode, suna hai? Tunnel diode, Zener diode, there the level of doping is also high, this much. But ordinary p-n junction diode जो rectifier circuitry में use होता है, there the doping level is very low. It is not to this level. But when we make a laser diode, we take a Zener diode, we take a tunnel diode, the doping of level is very high to the extent that Fermi level lies inside the energy bands. Okay. So, here Fermi level in N-type material is here EF in N-type, and here Fermi level is EF in P-type material. Okay. And when we make a junction, then what happens again similarly, electron will flow from higher field side to lower side, and electron are filled up to higher energy states in N side. So, electron will shift from N side to P side. Okay. So, and they will shift till the time Fermi level get aligned throughout the material. दोनों साइड में Fermi level same position पर आ जाना चाहिए. Okay. So, for that you have to draw the energy band diagram. So, for that again first you draw EF, you draw common EF, and then you take a junction point, and either side of the junction you consider the region from where and to where electron transfer has taken place. So, suppose this is the 2 junction, this is N side, and this is the portion of N side from here to here, from where electron has transferred from N side to P side. Similarly, you take portion of the P side where electron has come from N to P side. Okay. So, you choose 3 points: junction, true junction between P and N, and the side regions between which electron transfer has taken place, right. Now what you do on these regions, this side in P type material, left side, extreme left side is the portion where no electron has come from N side. So, you draw energy level diagram there. So, this is EF. In this P type Fermi level, EB should be here. Okay. EB should be here, and EC should be EG up. EC कहाँ जाएगा? EG ऊपर. Okay. You draw EG. EC. Now you draw conduction band, valence band in N side where no electron has shifted, from where no electron has shifted to P side. Okay. And that situation is this, the initial situation. Okay. So, here you will have EC here and EG down, right. Now, you join EC to EC and EB to EB. Okay. So, you join EC to EC here and you join EB to EB here. So, this is the band diagram now, and you show it like this. ये जो शेड पोर्शन शो किया है विद शेडेड काइंड ऑफ थिंग, दिस पोर्शन शोज फील्ड एनर्जी स्टेट्स. ओके. ये जो बार शो कर रहे हैं ये इस तरह से, जो शेडेड पोर्शन है, क्या कहेंगे इसको? दिस इज द रीजन फुल ऑफ इलेक्ट्रॉन्स, द बैंड फुल ऑफ इलेक्ट्रॉन्स, एंड remaining portion here you see empty states, here you have empty states. Okay. So, you get here energy band diagram like this. Now, you see here near somewhat away from junction you have enough concentration of electrons in conduction band, and you have enough concentration of holes in the valence band on P side away from the junction, junction से थोड़ा दूरी पर. Okay. So, this is the PN junction we will take to make a laser action. Now, we apply forward bias. Applying forward bias means you are connecting P to positive and N type to negative. Okay. And when you apply forward bias in this diode, you have two things. One is this you called W depletion layer width, and here it is called VBI built in potential. Okay. Means when electron transferred from N side to P side, N side become positive, N side left positive due to positive ions, or P side becomes negative. Okay. So, when N becoming positive, P becoming negative, electric field is created. Okay. So, when electric field is created, P side get negatively charged. Now, this negative charge which build up, it stops further transfer of electron. So, एक balance बन जाएगा. Initially, electron will be transferred from N side to P side, but as electron get transferred, furthermore transfer reduces. और एक ऐसा situation आ जाता है कि transfer of electron from N side to P side एकदम रुक जाएगा. And that is due to opposition of electric field developed due to earlier shifted electron. So, it means when positive negative potential is created, so there becomes potential difference created between P side and N side. So, this is the potential barrier that is created, that now electron from N side to P side can't go because they are repelled by the negative charge on N side. तो एक potential develop हो जाएगा. This is called built-in potential, VBI. Okay. So, we have two parameters in a diode: built-in potential. Built-in potential is the shift between the energy bands. How much energy band shifted in P side respect to N side. N से P side में EC कितना shift है और EV कितना shifted है. ये जो shift है, it is equivalent to this barrier, and this is the depletion layer width. Depletion layer width already we have discussed. So, this is the depletion layer width. Now, when you apply forward bias, what happens to these two? You may be knowing. As you apply forward bias, depletion layer width decreases and built-in barrier also decreases. Okay? So, it means when you apply forward bias, ये जो band bending है ये थोड़ा कम होगा. N side conduction band will lift slightly up and P side conduction band will lift slightly down. As you apply more and more electric field, ये जो shifting है ये कम होता जाता है. Okay? And at the same time depletion layer width भी reduce होगा. And the moment depletion layer width reduces, the two regions approach each other. Two regions कौन से है? Region where you have enough electrons in the conduction band on N side, and here region where you have enough holes in the valence band. So, ये जो दो regions हैं, these two regions are near the junction, away, slightly away. जंक्शन से दूर है, बट व्हेन यू अप्लाई फॉरवर्ड बायस ये रीजन एक दूसरे को अप्रोच करेंगे ड्यू टू फॉरवर्ड बायसिंग. ओके, सो वी विल नाउ ड्रॉ दिस एनर्जी लेवल डायग्राम अगेन अंडर डिफरेंट फॉरवर्ड बायसिंग. ओके, ये नो फॉरवर्ड बायस है. नाउ वी विल अप्लाई सम लिटिल फॉरवर्ड बायस, देन लिटिल मोर फॉरवर्ड बायस, then more forward bias, just to understand what happens, how the energy bands takes the shape when you apply different biases. Okay, so for that we will just draw different diagrams. So let us see how it will appear. You will have something like right. So you can say here VF0, no forward bias. Okay, let us say VF1 not equal to 0, VF forward bias 1 not 0 but little bit. Okay, you call forward bias 2 VF2 greater than VF1, VF3 greater than VF2, right. So, for some forward bias, more forward bias, still higher forward bias. Okay? And as you apply forward bias, the bending will decrease. The difference between shifting जो है EC और EC on both sides कितना shifted है वो कम होता जाएगा. Band will lift like this. Okay? So, you will see the situation somewhere like this. So, can you notice the difference here between these different diagrams? What you will see, the region where you have enough electrons and you have enough holes, they are widely separated. But when you apply forward bias, the two regions approach each other. They move towards the true junction. So, at some little bias, they will appear like this. But when you apply more forward bias, they appear like this, that they approach the junction. Just junction per one side you have enough electrons, other side you have enough holes, just as at the junction, at this bias. But इससे पहले क्या था? They were far away from the junction. They were separated. But when you applying forward bias, the regions are approaching, and situation will come that they will start overlapping. When you apply higher forward bias, the region starts overlapping. Junction पर situation create हो जाएगा where you have enough electrons in the conduction band and enough holes in the valence band. Enough electron in the conduction band means higher energy states are occupied. Holes in the valence band means lower energy states are empty. So, you have higher state filled, lower state empty, means higher state have more population, low states have less population. It's kind of population inversion. और जब ये situation होगा, what will happen? Electron from conduction band will fall down to vacancy holes in the valence band near the junction, and we expect during this transition energy should be released in form of radiation. Okay? So, here this energy radiated in terms of photon will be taken as a output. Okay? This is what the energy radiation emitted in diode due to electron hole recombination. When electron in the conduction band recombine with the hole in the valence band, and it happens at certain bias. This is called threshold position, starting position. Okay? इस position पर आपका ये एक process शुरू हो गया where some emission takes place. Okay? So, in LED we get this light emitted, light emitting diode, LED आप very much aware हैं. So, LED में we get this light emitted due to this overlap, and this is initially spontaneous emission. Okay? When electron are in the higher energy state conduction band, they see low energy states in valence band unoccupied, they jump from conduction band to valence band, emitting extra energy in form of radiation, what we call LED operation. Population inversion means more states, more electron in higher states, less in ground state, lower state. Valence band, yeah. Yes. This part of the valence band is unoccupied. ये जो valence band ये जो shown किया heavily doped semiconductor में, this portion of the valence band is unoccupied, means low energy states are empty, right? So, higher energy states are occupied, low are empty. So, electron will see low states empty, higher state occupied, they will jump down. But ये कब होगा? When it happens at a same point, junction पर. यहाँ नहीं हो सकता, यहाँ भी नहीं होगा. Initially at zero bias it will not happen, because at zero bias or at low bias you have enough electron in the conduction band in n side, okay, and enough hole in the valence band on p side. So electron have to go from n side to p side, passing through depletion region, है ना. तो उस समय नहीं होगा. It will happen, this recombination will take place when this overlap begins, when carrier are forced from n side or p side to move towards the junction. Junction पर एक ऐसा point आ जाएगा where you have higher states occupied, low states empty. तो यहाँ पे recombination शुरू होगा. इस पॉइंट पे नहीं होगा, बिकॉज इस पॉइंट पे इलेक्ट्रॉन हैज नो वैकेंसीज हियर, है ना. बट हियर इट विल स्टार्ट. ओके, सो दिस इज एलईडी ऑपरेशन. एलईडी लाइट emitting diode is this much, that you take a junction between heavily doped p and n material and you apply forward bias, you will get some light emitted as spontaneous emission. Okay, but to get laser light we have to make it more intense, and that how we can do? For that heavily doped is already there. Okay, heavily doped is already there because that we have considered. Now you think of a block, एक small block ले लेते हैं. Okay, you take a block of semiconductor and suppose you make the top portion p type and lower one n type. Okay, एक block है, top portion is p type, lower one is n type. So where this happen? ये कहाँ होगा? Where this overlap take place? It take place at the junction. Okay, so that you can see here. This is the rectangular slab. Okay. This is the rectangular slab where it happens. Agreed? Yes? Clear है या नहीं? मतलब ये situation कब कहाँ, where it will happen? It will happen at the central portion and that portion is like a slab, है ना. Okay, and that slab it is से एक तरह से पूरा इसको इस तरह से होगा ये. Okay, and everywhere in this region, everywhere this situation is happening. Okay, suppose here some electron hole recombines, some radiation is emitted in term of photon. Okay, तो यहाँ पे जब when this photon emitted, it will travel this way. So if it travel this way, what we will do? We will make this phase reflecting, this phase also reflecting. This is a 50 to 80% reflecting. ये जो side face है, and this side face is 100% reflecting. Okay. Now any photon emitted along this x-axis इस तरह से, what will happen? It will propagate through the semiconductor. ये semiconductor से जाएगा and this travelling photon may strike another electron which is here, because ये situation is prevailing at everywhere. So when this travelling photon hits some another electron in the conduction band, it will force this electron to come down by stimulated emission, and you will have two photons. When these two photons further travel, you will get multiplied. Okay, and here they get reflected. Some get reflected and some are allowed to transmit. जो transmitted ray होगा, that will be our output beam, and part will be reflected. Reflected photon again travel through this depletion layer, and inside the depletion layer you have this population inversion. So there will be more and more multiplication, stimulated emission. When they reaches here after multiplication, all get reflected. Okay, so again they multiply. Okay, so this way we put here side surfaces reflecting mirror. Okay, and here we apply bias. P N. ओके, तो बैटरी हमारा किधर लगा है, बाइसिंग वोल्ट इस तरह से. सो अगर आप एक ब्लॉक लेंगे, ओके, ब्लॉक लेंगे तो आप एक डायरेक्शन में आप बायस लगाएंगे. When you create a bias, central portion you create a depletion region where there are overlap of these high electron and low high concentration electron, high concentration of hole. है ना? The region will overlap and that overlapping region will be kind of a rectangular slab. Okay, and here side faces we put mirrors. So these reflective mirror, they are placed, they are kept for making a laser. Okay, so in laser this is the additional arrangement. LED mein there is no such arrangement for reflecting mirrors. The light spontaneously emitted photon, they will give you some light, but in laser we put reflecting mirrors. Due to this reflecting mirror, more multiplication takes place and you will get intense laser beam. तो difference laser beam और आपके LED में क्या है, यही है कि there is provision for reflecting mirrors in the laser diode. LED में वो provision नहीं है और LED light emitted है, it is due to spontaneous emission, but laser light emitted due to spontaneous emission, stimulated emission, right? And difference अगर आप देखेंगे तो if you take LED तो आप daily use में देखते हैं, laser भी देखा ही आपने. तो when you take a LED and laser, तो LED की लाइट यहीं दिखाएगी आपको, LED के ऊपर ही दिखेगी, वो कहीं जा नहीं सकती, बिकॉज वो स्पॉन्टेनियसली इमिटेड है एंड इट इज़ रैंडम फेज है, इट इज़ नॉट कोहिरेंट. बट जो लेज़र बीम इज़ हाईली कोहिरेंट है, तो अगर आप यहाँ से लेज़र ऑन करेंगे तो इट कैन ट्रैवल किलोमीटर डिस्टेंस, यू कैन सी ए बीम, शार्प बीम ट्रैवलिंग. बट LED में कुछ नहीं दिखेगा. सो LED को एज ए इंडिकेटर यूज़ कर सकते हैं कि वो वहीं लाइट दिख रही है, तो LED को एज ए इंडिकेटर यूज़ कर रहे हैं कि हाँ ठीक है, समथिंग सिस्टम ऑन है, लाइट है, दैट इज़ लाइक ए इंडिकेटर. बिकॉज लाइट इमिटेड इज़ नॉट वेरी इंटेंस, इट कैन नॉट ट्रैवल, वो कहीं नहीं दिखेगी. अगर आप LED के सामने हाथ रखेंगे तो आपके हाथ पे कुछ लाइट नहीं पड़ेगी, हार्डली थोड़ी सी पड़ेगी, नहीं तो नहीं पड़ेगी. बट लेज़र जो है, आप अगर यहाँ से लगाया तो आपकी फ्रंट वॉल पे भी वो आपको उसका हाई इल्यूमिनेशन you will see. So this is main difference between LED and laser diode. So there are similarities, there are dissimilarities. Similarity क्या है? LED laser diode both are heavily doped PN semiconductor made, both acts in forward bias, but in laser diode there is provision for reflecting mirror. In LED there is no such provision for reflecting mirror to create stimulated emission. ठीक है? LED में only spontaneous है, laser में we get stimulated emission. Okay? So this is how the laser diode formed, how it works. Any questions so far? We will see some more aspect of this. But this is a brief mechanism that how we take a heavily doped material PN junction and how junction is formed, and then how we get this light emission. Population inversion कैसे create होगा with biasing, उसके लिए you can see this. So up to here any question?
Sir, the heterojunction laser और इसमें difference क्या होगा?
We will come to heterojunction. Yeah. We will come. So any other point basic related to basic working? If not, then let's proceed further. So here in laser diode, LED or laser diode, we expect that when electron jump from conduction band to valence band, it should emit light, it should emit radiation. Okay? Now our popular semiconductor, silicon, germanium, they will not do so. You will not get light emitted here. Okay, so we cannot make LED or laser with the help of silicon, germanium. And reason for this, वो क्या है? उसके लिए थोड़ा सा we have to see in detail. So you see these semiconductors, they are crystalline solids, and in crystalline solid atoms are arranged periodically. Okay, they are arranged periodically in space, and electrons are moving through these atoms. जो atoms हैं, atoms are making a solid arrangement fixed in space, and electron donated by these atoms, atoms से ही निकले electrons हैं. Okay, so electrons donated by these atoms, which are available as conduction electrons, they move through the solid. वो solid के through move करते हैं through these free space between the atoms. तो आपके पास एक compact lattice है जिसमें atoms are periodically arranged, और उसमें बीच में गैप स्पेस के थ्रू होकर आपके इलेक्ट्रॉन मूव कर रहे हैं. एंड बिकॉज ड्यू टू दिस पीरियोडिक पोटेंशियल ऑफ एटम्स, एटम्स आर पीरियोडिकली अरेंज्ड इनसाइड द सॉलिड, देयर इज पीरियोडिक पोटेंशियल. ओके, व्हेन इलेक्ट्रॉन्स आर डोनेटेड बाय द एटम्स, then you left with the positive charge there. So there is positive charge in space, and electron is in motion in the periodic potential of these atoms. So ये जो periodic potential में electron motion जो होता है, उसमें we consider electron motion inside the solid like a wave. इलेक्ट्रॉन को सॉलिड के अंदर एक फ्री पार्टिकल की तरह से हम ट्रीट नहीं कर सकते. ओके, अकॉर्डिंग टू डी ब्रोगली हाइपोथेसिस, जैसे आपके रेडिएशन का ड्यूल नेचर है, तो अकॉर्डिंग टू डी ब्रोगली हाइपोथेसिस मटेरियल पार्टिकल का भी ड्यूल नेचर होता है, और दिस ड्यूल नेचर ऑफ मटेरियल पार्टिकल इज मच प्रोमिनेंट व्हेन दिस m into m and a, mass of the particle, and a the distance to which it is confined, mass and a, ma, if it is comparable to h के comparable है, then more this ma factor is more close to h, more likely the particle will behave like a wave. Okay, more likely that particle will behave like a wave. So mass of electron is something 10 to the power minus 31 kg, and it is confined to angstrom distances. Okay, so angstrom distances में then when electron is confined, then 10 to the power minus 10 distance हो गया, और mass हो गया आपका 10 to the power minus 31. Okay, so ma is something 10 to the power minus 41, और h square is 10 to the power minus 66 के करीब, h square, हाँ, h square upon ma है. Okay, when ma is comparable to h square. Okay, अगर आप लेते हैं one ball of 1 kg, okay, confined to 10 meters, एक बॉल 1 kg बॉल को या 100 ग्राम बॉल को 0.1 kg 100 ग्राम बॉल you throw a distance of 10 meters. So distance to which it is confined 10 meter, और इसका मास है 0.1 kg, तो ये कितना हो गया, 1 हो गया. So 1, और यहाँ पे h स्क्वायर आपका कितना है 10 to the power minus 66, but electron confined to angstrom distance. When electron confined to angstrom distance, तो ma की वैल्यू आई 10 to the power minus 41. So we can say 10 to the power minus 41 is much closer to minus 66 as compared to 1, है ना. So electron inside the solid behave more likely like a wave, और उनको वेव कंसीडर करने के लिए हम उसको क्वांटम मैकेनिक्स की हेल्प से श्रोडिंगर वेव इक्वेशन लगाकर उनको सॉल्व करते हैं. वी कैन नॉट अप्लाई न्यूटन्स लॉ, वी कैन नॉट टेक मोशन ऑफ इलेक्ट्रॉन लाइक ए न्यूटोनियन पार्टिकल. उसको एक लाइक ए वेव ट्रीट करना पड़ेगा. इलेक्ट्रॉन बिहेव लाइक ए वेव, ठीक है ना. सो व्हेन इलेक्ट्रॉन्स इनसाइड द सॉलिड बिहेव लाइक ए वेव, तो जहाँ पे ये ड्यूल नेचर एग्जिस्ट करता है मटेरियल का, तो ड्यूल नेचर को कनेक्ट करने वाली एक प्रॉपर्टी है, एक इक्वेशन है, दैट इज वी हैव P इक्वल टू H बाई लैम्डा. You have a relation where you have P equal to H by lambda. P is the momentum of the particle and lambda is the wavelength associated with that particle. कोई particle है, if it is behaving like a wave, then wavelength is lambda. तो wavelength is a wave property and momentum is a particle property. Okay, and P equal to H by lambda, it relates wave property to the particle property. तो सेम रिलेशन फोटोन के लिए है और सेम रिलेशन हम इलेक्ट्रॉन के लिए भी लगाते हैं. सो यू हैव दिस रिलेशन एंड यू राइट लाइक दिस 2 पाई. सो h अपॉन 2 पाई यू राइट h क्रॉस and 2 pi by lambda we write k the wave vector. Okay, so we have here P equal to h cross k. Now you know energy of the particle is p square by 2m. So in term of wave property, this will be h cross square k square upon 2m. Okay, so ये रिलेशन हुआ एनर्जी और वेव वेक्टर के बीच, और यहाँ एनर्जी और मोमेंटम के लिए है. Okay, so here E, when we consider motion of electron like a wave, तो रिलेशन हुआ E equal to h cross square k square by 2m. तो यहाँ से हुआ k square equal to twice m upon h cross square and E, and it is like a y square equal to 4ax. Okay, so means relation between energy and wave vector. रिलेशन बिटवीन एनर्जी एंड वेव वेक्टर, और k जो है from here k is related to momentum, right? So either you talk of k or you talk of momentum, because momentum and k are linearly related. Okay, so relation between energy and k is like a parabola. Okay, energy and k और एनर्जी एंड मोमेंटम. मोमेंटम बोलेंगे तो थोड़ा हमें चीज़ों को समझने में इजी रहेगा. ओके, बट रिलेशन के साथ है, और के और मोमेंटम जो है लीनियरली रिलेटेड है. तो सिंपली लेट अस से दैट एनर्जी एंड मोमेंटम जो है पार्टिकल का, relation between energy and momentum is like a parabola. There is parabolic relation between energy and momentum. Okay, it means when electron is traveling inside the solid, you observe its momentum and you observe its energy. जब ये क्रिस्टल के अंदर इलेक्ट्रॉन मूव करेगा, तो आप किसी भी मोमेंट पे किसी भी डायरेक्शन में जाते हुए you observe electron energy and you observe its momentum. Okay, so you can know it at different points. So because electron is moving inside a periodic potential, crystalline solid के अंदर है, तो when it is moving in a crystal, its momentum in different direction will be different because it see a different environment. आपका FCC solid है ना, FCC BCC solid है, तो उसमें आप you will see arrangement of atom is different in different direction. तो जब आप एक इलेक्ट्रॉन मूव करेगा, it will see different environment of atoms inside in different directions. तो जब इलेक्ट्रॉन मूव करते हुए it will appear different momentum in different direction. Now you record energy as well, and when you plot energy and momentum, EK plot, it is called EK plot, you will find it is like this. You have this K and this is E. Okay, E and K. So E and K is like a parabola. So you may have some plot, something maybe like so you take different crystals, okay, and you start किसी पॉइंट से आपने किसी यूनिट सेल के कॉर्नर से मूव करना शुरू किया किसी एक डायरेक्शन में. 100 का मतलब है एक्स एक्सिस के लो लैटिस पैरामीटर. ये पढ़े मिलर इंडिसेस पढ़े आपने? ओके, यू टेक इट लाइक दैट एज इफ यू आर मूविंग इन वन डायरेक्शन and you are moving in some other direction, and you record the momentum of the electron and energy as well. And when we plot energy momentum, it is like a parabolic plot. Okay, energy, ये energy है, तो ये when you plot this, it is like a parabolic shapes है. Energy and momentum is a पैराबोलिक शेप्स होती है. दिस इज कॉल्ड EK डायग्राम. ये थोड़ा सा एडवांस सब्जेक्ट है, सॉलिड स्टेट फिजिक्स में आप कभी पढ़ेंगे अगर पढ़ते हैं, बट बिकॉज फॉर फंक्शनिंग ऑफ लेजर इट इज लिटिल बिट रिलेटेड. इट इज वेरी मच रिलेटेड बट यू नीड टू नो लिटिल बिट ऑफ इट. आई कैन से दिस. ओके, ग्राफ इज इंटरप्रेटिंग that when electron is moving inside the solid, when it is moving, its momentum and energy are changing. Okay, its energy and momentums are changing. It will have different energy, different momentum at different point in space when it is moving inside the crystal. Okay, and those curves are like this. ठीक है. So we simply conclude up to here that energy versus momentum, energy versus K plots are parabolic shapes. Okay. Now let's come to conduction band, valence band. जब हम बोलते हैं कि conduction band energy, electrons have energies in the conduction band, वो जो conduction band हमने draw किया है, those conduction band means those energies which electron can have. Now you have to see that energy versus momentum. Okay, so in these energy versus momentum plot you will find two different things. Two main differences are there in these plots. वो differences क्या हैं? For example, this is the conduction band energies, this is the valence band energies. मतलब energies of electron inside the valence band जो हैं वो ये values हो सकती हैं corresponding to different momentum. Okay. So here is the minima of the conduction band, maxima of the valence band. Here is the minima of the conduction band and maxima of the valence band. Okay. So here minima of conduction band, maxima of valence band occurring at different K. Here minima of conduction, maxima of valence band occurring at same K. There are two type of curves materials के लिए. Material will have either these type of plots or these type of plots. For example, silicon germanium has these type of behavior. Gallium arsenide ये गैलियम है और जर्मेनियम. Now see, this is the minima of conduction band energy. Now this minima occurring at this K. Okay, and this K means somewhere positions. क्योंकि ये K कहाँ होगा? ये कहीं, because K related to its position. Okay, so what electron will do? Electron inside the solid will get accumulated with minimum E. सॉलिड के अंदर से इलेक्ट्रॉन जो है सारे वहां से शिफ्ट होके कहां पे, किस पॉइंट पे आ जाएंगे, वेयर द एनर्जी इज मिनिमम. गॉट इट? दैट इज द रेलेवेंस हियर. So electron from the nearby portion will come accumulate at position where you have E is minimum. This is the conduction band minima. Okay? And holes inside the solid, valence band के अंदर जो holes है, hole will accumulate in the region where the maxima of this valence band is there. Hole is like a bubble. Hole is like a bubble in कंटेनर वाटर बकेट है, उसके अंदर अगर आप इफ यू पुट ए होल कहाँ जाएगा, ऊपर जाएगा. होल विल रिमेन ऑलवेज अप. सो बबल ऑलवेज रिमेन्स अप. सो होल इज लाइक ए बबल. ओके. एंड इलेक्ट्रॉन इज लाइक ए सैंड पार्टिकल. इलेक्ट्रॉन इज लाइक ए सैंड पार्टिकल. यू पुट ए सैंड पार्टिकल इन जग ऑफ वाटर, सैंड पार्टिकल नीचे सेटल होगा. सो इलेक्ट्रॉन विल ट्राई टू सेटल लोअर एंड लोअर, होल्स विल ट्राई टू सेटल अपर एंड अपर. बेसिकली होल जो यहाँ पे हैं तो वो अपर कैसे हो रहे हैं, क्योंकि यहाँ पे इलेक्ट्रॉन जो हैं दे विल कम टू वैकेंसी. होल इज वैकेंसी. सो हायर एनर्जी इलेक्ट्रॉन विल कम टू लोअर होल एंड होल विल शिफ्ट अप. दैट्स हाउ इट हैपन्स. Okay, so inside the crystal all holes will get accumulated in near the top of the valence band. Okay, and all electron accumulated here near the minima of the conduction band. And whenever there is transition from conduction band to valence band, it will be from minima of the conduction band to maxima of the valence band. Okay, तो solid के अंदर जो इलेक्ट्रॉन होगा, फर्स्ट ऑल इलेक्ट्रॉन इन द सॉलिड दे गेट सेटल्ड टू द लोअर एनर्जी. तो लोअर एनर्जी वो एक जगह इकट्ठे हो जाएंगे, वहां से फिर वो एक्स्ट्रा एनर्जी रिलीज करेंगे और लो एनर्जी एक्वायर कर लेंगे कोरस्पॉन्डिंग टू वैलेंस बैंड एनर्जीज. ओके. सो हियर इट विल हैपन लाइक दिस. नाउ इन द टू ट्रांजिशन यू विल फाइंड हियर इफ इलेक्ट्रॉन हैज कम फ्रॉम हियर टू हियर इन दिस अरेंजमेंट. अगर सॉलिड आपका इज ऑफ दिस टाइप एंड व्हेन इलेक्ट्रॉन कम फ्रॉम हियर टू हियर, it has to change its momentum k. Okay, if electron come from here to here in this diagram, it has to change its momentum, but here it is not required. In this arrangement there is no requirement for changing the momentum. So when electron jump from conduction band to valence band, some of its energy transfer to get momentum change, because energy momentum has to be conserved. Energy and momentum जो है वो टोटल कंजर्व रहेगा. तो मोमेंटम चेंज करने के लिए कुछ एनर्जी उसकी वहाँ पे ट्रांसफर हो जाएगी टू मेक मोमेंटम चेंज. एंड मोमेंटम चेंज कैसे होगा? फॉर मेकिंग मोमेंटम चेंज देयर मस्ट बी कोलिजन प्रोसेस. इलेक्ट्रॉन विल कोलाइड विद द लैटिस एटम्स. जो वाइब्रेटिंग लैटिस एटम्स हैं, atoms inside the solid. So electron will collide with the lattice atoms, and when it collide with the atoms, it will release its energy. It will lose its energy. So that energy will be loose in form of heat. That energy will be loose in form of heat, because to make momentum change. And here there is no such requirement for momentum change. Electron will simply release its energy, keeping the momentum same. And in this transition, this energy released will be going in form of h nu, but here it will be going in form of heat, right? So if the band arrangement, band gap arrangement, if it is like this, it is called indirect band gap, and it is called direct band gap. Okay, so silicon, germanium, they are indirect band gap semiconductor. They are not good light emitter. Whenever electron combine in silicon, germanium, you will not get any wavelength emitted. They are not good light emitters. Yeah, it won't. Okay. So, gallium arsenide, their light will energy will be emitted in form of radiation. So, to make a laser diode, we have to use direct band gap semiconductor. This is the second most important difference, that to make a laser diode, we have to make use of semiconductor which is having direct band gap type. Okay? Or you can say where light can be emitted in term of energy can be released in form of radiation. Thus, when electron from conduction band combine with the holes, this energy release should go in form of radiation, and that happens in these type of semiconductors. Okay, so that is this another requirement. So, you have two diodes, conventional diode which you use as a rectifier, and this is a laser diode. So, laser diode, it must be heavily doped, it must be made up of a direct band gap semiconductor, laser diode. But जो आपका rectifier diode है, that can be of any type, because there is no requirement for light emission. Okay, I think time over है. I think little bit we will continue. Heterojunction aspect हम थोड़ा next time इसको touch कर लेंगे.